Here's a problem for you. Scientists have developed a new drug that can target a single, specific mutation that appears in cancer cells. Healthy cells don't have this mutation, so this drug has the potential to treat someone's cancer while avoiding all of the side effects associated with other cancer treatments. What's even better is that several cancers have this mutation. This opens up the possibility that many different cancers can be treated with just a single drug. But here's the rub. Even though different cancers can share the same mutation, we wouldn't expect this drug to work in most of the cancers that have the mutation. Each cancer has its own unique biology and could have other mutations that can hurt the drug's effectiveness. Despite this, it would still be worth it if we could identify even just one cancer where the drug is more effective than the current standard of care. We'll call this single cancer group the nugget. If we can identify this nugget, we're one step closer to getting the drug approved for human use and saving lives in the process. Of course, we don't know which cancer group is the nugget, and we have a lot of groups to deal with at the same time. This is where you, the statistician, comes in. Given a large number of cancer groups, and one nugget among them, propose a statistical model to give yourself the best shot of identifying the nugget. In this case, we're not doing comparisons. We're only interested in precisely estimating the proportion of people that see a significant reduction in tumor size in each group. We'll call this the response rate for each group. Keep in mind that some cancers are rare, so some of the groups might only have a few people we can recruit. If you're new here, my name's Christian and this is Very Normal, a channel for making you better at statistics. In my opinion, to really understand statistics, you should understand some of the unique and interesting problems that statisticians face. This is one of those problems. Let's get started. So the goal of the analysis is to get a precise and accurate estimate of the response rate for the nugget. In statistical terms, we want an estimate that has 1. Low bias, and 2. Minimal variance. Low bias means that our estimate for the response rate should be pretty close to the true efficacy of the treatment, and low variance means that our interval estimates will be as small as possible. To help ground our thinking, I've simulated a dataset with 36 different quote-unquote cancer groups. Each group will have between 10 and 30 people. The response rates for the non-nugget groups will be 20%. We'll consider this to be a sort of baseline response rate, the proportion of people in each group whose cancers will improve without any treatment. The nugget will have 9 people, but the response rate of this group will be 60%. It's the 60% that we want to estimate as closely and precisely as possible. In reality, we'll never know the response rates for any of these groups, or which one is the nugget, but it'll help show you how different models can influence our estimates. One way to get low bias and minimal variance is to maximize the number of people in the analysis. So, a natural approach you might take is just to ignore the fact that these 36 cancer groups are different and combine everyone into a single analysis. In other words, estimate a single response rate for all 36 groups based on all the responders and people in the data. This is called a pooled approach, since we're pooling all of the data into one supergroup. In this script, I've written a Bayesian version of the pooled analysis using Stan. Stan is a popular programming language for Bayesian analysis, but I won't be going into the particulars here. The main takeaway is that my model will only have a single posterior distribution for the single pooled response rate. I can summarize all of the information in this posterior into an estimate for the response rate through the posterior mean, which is about 22%. This 22% is supposed to represent the estimated response rate for all 36 groups. And hopefully that makes sense. We have 36 groups, and all but one of them have a true response rate of 20. By grouping all of the data together, it'll make it seem like the overall response rate is close to 20%. But remember that the response rate of the nugget was 60%. The pooled analysis produces a close estimate for the non-nugget groups, but it totally screws up the estimated response rate for the nugget. We get a bias of 38% here. If we were to use the pooled analysis, we would completely miss the nugget and our chance to get it approved for this particular cancer group. We get the benefit of a really small credible interval, but what's the point when we miss the nugget altogether? So ignoring the inherent differentness in the cancers produces bad results. Now we know. Instead of clumping everyone into one big group, we could let each group have its own response rate. This approach acknowledges that each group is a distinct cancer, and it would be called an independent approach. Like its name suggests, the independent approach assumes that the response rates for each group do not influence or are related in any way to the other groups. It only uses the data for a particular group. You can think of the pooled and independent approaches as two extremes on a continuum. Either all the groups have the same response rate, or they have their own distinct rate. Here's a Bayesian implementation of the independent approach in Stan. Again, you don't need to understand it to get the video. All I want to point out is that each group gets its own response rate. Similar to the pooled approach, I'm using an uninformative beta prior for the response rate and a binomial likelihood for the data. After running this model, I get the following estimates for the response rates. You can confirm that each group has its own response rate, but also that these rates vary way more compared to the pooled approach. For the non-nugget groups, the estimated rates go as low as 11% all the way to 43%. So some of these non-nuggets start to look like prospects when they're actually not. In a phase 2 setting, that's not the end of the world. You just might waste some money in other trials trying to confirm what you saw here. More importantly, if you take a look at the nugget group, you can see that it has an estimated response rate of about 50%, the highest out of all the groups. Therefore, an independent approach would definitely help identify the nugget group for future studies. The bias for the independent approach also drops to 10%, much better than the 38% we got in the pooled approach. But remember, we had a twofold goal. We're not just worried about the bias, but also the variance in the posterior. Even if our results are on target, it's not useful if they're all over the place. Here's where we can start to see some weaknesses in the independent approach. Compared to the pooled approach, the posterior distributions from the independent analysis are much larger. What's the cause of this? Smaller sample sizes. In the pooled analysis, we could take advantage of a total sample size of about 700 people. But in the independent analyses, we're only working with groups between 9 and 30 in size. You can see that there's what's called a bias-variance trade-off between the pooled and independent approaches. You can try to get a lower bias for the nugget group with an independent approach, but it raises the variance of the estimated rates. This is a common phenomenon that appears in many areas of statistics, and it forces statisticians to be mindful of the models they use for analyses. If we were to stop here, you might conclude that the independent approach is the way to go for the nugget problem. And you wouldn't be wrong, it works. But I challenge you to dig deeper. Can you think of another approach that might improve on the bias or variance of the nugget response rate? Let's take one step further and see another way we can move beyond the pooled and independent approaches. The independent approach is an improvement because it acknowledges that each cancer group should have its own response rate. But it also ignores the fact that they all share a common mutation. This is potentially useful information that we can incorporate into a model to produce even better results. That being said, how do we do that? To set up this new approach, let's take the response rates for each group and put them on a number line. Consider a world where the mutation is the major reason that the drug works. In this world, the drug can target the mutation so strongly that all the cancers will have a similar response rate despite the fact that they're different. They won't be exactly the same, but the strong drug-mutation interaction leads them to cluster pretty closely around some point. You could think of this point as an average response rate thanks to the drug. But now let's consider a different reality where the different aspects of the cancers start to change how they react to the drug. For some cancers, their specific characteristics make the drug less effective, pushing the response rates lower. In others, these differences might make the drug more effective, leading to higher response rates. That is, the individual differences in the cancers here lead to a wider spread than the response rates. These response rates could be wildly different, but there's still some average response rate that arises out of the distribution of points. Something we can do to model this idea is to model the response rates themselves as coming from a distribution. This distribution allows each group to still have their own response rate, but encodes our knowledge that there are mechanisms driving them to be similar or different. In this example, the shared mutation drives the rates closer, and the genetic and environmental differences between the cancers drives them apart. For simplicity, we'll model the distribution of the response rates with the normal distribution. There's a mean that represents the average response rate that the drug will evoke, and there's a variance that represents how different these rates can be. This type of model has a special name, a hierarchical model. The one I've described here is just one of many different types of hierarchical models that are possible. Like its name suggests, there are stages to this model. At one stage, there's a distribution that dictates how well the cancers respond to the drug. It governs the response rates. Once each group has their own response rate, the next stage is the data we observe for each of the groups. In this case, binary variables representing whether or not someone responded well to the drug. Hierarchical models allow us to do what's called partial pooling. In the pooled approach, the pooling happened at the level of the data. Everyone is tossed into the same pool. In partial pooling, the information is shared through the estimated response rates. Each point on this line tells us about the variance in the first stage. And as you'll see later, this has downstream effects on the estimated response rates. Andrew Gelman listed hierarchical models as one of the most important statistical inventions in the last 50 years, and for good reason. Wherever you have clusters or groups of related things, a hierarchical model is a good approach you can use. I've created a simple Bayesian hierarchical model here. It's similar to the independent model, but here you can see that there's now a distribution on the rates themselves. I'm doing some reparameterizing here so that it plays nicely with the normal distribution, but it's not really the focus here. Here's a comparison of the posterior means estimated by the hierarchical model shown in red and the independent model shown in blue. You can see that the response rates of the non-nugget groups have an increase in their estimated response rates. On the other hand, the nugget response rate remains relatively the same. This phenomena is called shrinkage, not the kind you're used to in a cold shower. It's easier to see the shrinkage on the number line. Here are the response rates we got from the independent approach. The distribution assumption on the response rates has a tendency to bring all the rates closer to the average response rate. But in this case, the rate of the nugget group is an outlier among the other groups. It shifts the average higher, pulling the other rates along with it. This helps to reduce the bias in some of the groups, but increasing it in others. We also get a smaller credible interval with the hierarchical model as well, compared to the independent analysis. To summarize all of this, we have better results for the nugget, and we have mixed results for the non-nugget groups. But we're just looking for the best estimate of the response rate for the nugget, so these results suggest that the hierarchical model is the best approach of the three we talked about. But taking a step back, this exercise was really a demonstration of the so-called no free lunch theorem. That is, no one algorithm is going to be universally best in all situations. In this particular situation, the hierarchical model seems the best, but we needed to establish some goals and assumptions on our toy dataset. In the real world, we'll have to compare different approaches and simulation studies that will help cover our bases on what we think a realistic scenario is. The moral of the story is that a more complicated model doesn't necessarily give you better results. A more sophisticated model should ideally be backed by expert reasoning or made to better fit the information that we have. To be honest, since the nugget is such an outlier, it seems a little weird to include it with the rest of the groups. I'd actually thought of a fourth model to include in this video, but I'm sick and I got tired of editing this video. So you know what model I'm referencing and the reason we'd want to use it? Then let me know in the comments. I'll be impressed. This video was inspired by Malcolm Gladwell's new book, Revenge of the Tipping Point. There's a phenomena called small area variation that gets brought up. It's the idea that pockets of a population can have wildly different behavior from their surroundings. This idea was similar to a problem I once read about, so it inspired this video. Lastly, if you like this video and want to see more, then I hope you'll consider subscribing to the channel. I try to put out a new video every 2 weeks. You can also get videos sent directly to your inbox if you sign up for the channel newsletter. I'll let you know when new stuff comes out, and you'll hear about what's going on behind the scenes with me and the channel. That's it for this one. I'll see you in the next one.